trained data. Here what I'm doing is a quick calculus lesson, an introduction to derivatives. We've been doing a lot with MT cars, and so I thought, if I was going to bring this into calculus, I could talk about derivatives of speed. The first derivative of speed is acceleration, and the second derivative of speed, which is the derivative of acceleration, is called jerk. I wanted to say torque, but torque is apparently more like angular momentum. So, why am I doing this? Derivatives are super important in data science. If, for example, you wanted to look at the relationship between sales and profit, you might create a maximizing function and find where the derivative is equal to 0, and that might be the point at which profit is maximized based upon on pricing, and that's something that we can get into later. But first, I wanted to do an introduction. How do you start doing calculus in a programming environment in R and RStudio? And this will be like an introduction to that. So position, for the first thing I'm doing is creating a vector called position, which is a list of numbers from 0 to 10, counted by 0.1. That's what this third argument is doing here. And then I'm calculating velocity as position cubed, and the derivative of velocity is 3 times position squared. You can do the math on the exponent here, bring it to the coefficient, and here jerk is the derivative of acceleration. And these final three are not as well known: snap, crackle, pop, but they're the further derivatives. And they have funny names, And so here we go. I'm going to plot it, GG title derivatives of speed. And here I can just keep adding geom lines for specifying the position over and over again, 0 to 10, but then changing the y values to reflect the function created by velocity, acceleration, jerk, snap, crackle, pop. And finally, I'm going to make this final line type dashed so that you can see the line underneath it, because crackle and pop here are both 0, so you can see them plotted on top of each other. A derivative, remember, is the change in a function over time. So speed is the change in position. Speed / velocity is the change in your position over time, but acceleration is the change in speed. It's the change in the rate of something. And derivatives are also important in financial modeling. I mean, people trade something that they call derivatives, where the price of that commodity or whatever depends on the price of something else. So here we go. I'm going to zoom out just a bit. Here is my graph, the derivatives of speed. The red here is that cube, and then the change in speed over time is acceleration. That becomes a little bit flatter, a little bit less of a dramatic line. And then when you get to jerk, that's the second derivative here. Here it's a totally linear line, and then snap is completely flat at 6. So the slope of these lines, and also the characteristic of them going from cube to linear to flat, because of you doing the process of differentiation, really changes the way in which you could look at something. So this was just an introduction into doing a little bit of calculus in a programming environment, and we're going to make use of some of these techniques later when we look at pricing and other stuff.